Okay, this is the review for Unit 7. In terms of Unit 7, we were on chemical reactions. A couple things that we did throughout this unit. One is we learned balancing reactions. We learned types of reactions. And then we went on an overview of the energy of reactions. And so I'm going to talk a little bit about the balancing and the types. If you want to learn more about the energy and how to diagram those with the bar charts, that's on the other video. So we kind of started this unit off with the nail lab. So we put the nails in copper chloride, and we found that there was a certain ratio of iron to copper, which led us to the understanding of balancing reactions. In this case, there was about 1 mole of iron for every 1 mole of copper. And so that held up consistently throughout every lab group's results. So from that, we were able to come to the idea that we need to have balanced equations. Now, the way we balance these equations is we know that 1 mole equals the same number of particles in a reaction. So remember that mole number is 6.02 times 10 to the 23rd particles. So if you have 1 mole of something and a mole of something else, the values are going to be the same. And so we started to represent that in the chemical equations by the coefficients. So these are the coefficients in the chemical equation. Now, in order to balance this, these were the reactants, and the products. Both of those had to have the same number of atoms of a certain type. So, for example, in this case, you have 1 carbon atom here, kind of in the black, and then there's one on the right side here on the right. We needed to have 4 oxygens here to balance the 4 that are over here. And then we also had to have 4 hydrogen atoms to balance the 4 that were over here. And so in order to do that, to balance these things, we needed to have 2 oxygen molecules. And so we put a 2 out in front of that. In order to balance the oxygens, we had 2 of those, and so we put a 2 as a coefficient there to balance this equation. So that led us into the balancing of equations, that we need to keep these things consistent. And balancing is really important also because we don't want to have excess amount of material like we did in the nail lab. I'm going to come back to this one here in a second. So here's the second way that I showed kind of how to balance things when they get more complicated, is to list them on the bottom. So carbon's listed here first, and always do oxygen last. And the reason why we do that is because this term is oxygen by itself, which can be balanced by itself without changing the other elements. So in this case, carbon is 1 and 1, hydrogen's 4 and 2. So this one needs to be added to the right side. So I'm going to put just a coefficient out in front here. So now my hydrogen becomes 4, but my oxygen also becomes a 4. And so now if I go, my carbons are good, hydrogens are good, my oxygens now need to be balanced. So I need 2 more over here. So to do that, I change this 1 term to a 2. This becomes a 4, and I've balanced my chemical equation. If you follow this process, like I said in class, you'll always get the right answer. The other way, the guess and check or visualizing it, that might be faster, but you'll always get the right way if you do it, the right answer if you do it this way. So then we got into what are some of the different types of reactions. Well, if you take one element and add it to another element to make one new compound, we call this synthesis. Sometimes we call it a combination or recombination reaction. Combination just meaning that you're combining 2 things. Synthesis meaning you're making something from 2 parts. The second one we looked at was decomposition. So remember, decomposers break things down. So in this case, we have one molecule, and that gets broken apart into the A and to the B. So those are two separate things. A single replacement is the next one. And a single replacement just means that usually the positive ion is going to replace the positive ion in a compound. So in this case, C is exchanging, and actually this one is written a little bit differently. So excuse my erasing there. C is going to replace B in this case. And so again, it's a single replacement because one atom is exchanging for another atom. Conversely, in the double replacement, you have two things that are exchanging. So in our start, we have AB here, we're going to have AC. We have CD here, we're going to have BD. So what that means is that we have these two are exchanging parts in the formulas. So now, when they exchange, A is free to match up with C, and B is free to match up with D. And there's many examples of this, but basically if there's two compounds here, A, B, and C, D, there's usually two compounds involved with a double displacement, whereas a single replacement is just one compound involved. And then, of course, the last one that we went over was the combustion one. I'm going to go back to the first slide for this because this is a combustion reaction. So I'm going to erase a bunch of this stuff here. So if we look at this reaction, there's a few certain parts that are important. In a combustion reaction, they always have oxygen. They always have CO2 as a product and water as a product. Those are the three fundamental parts of a combustion reaction. And they always start with some organic material. So organic is usually something with carbon, hydrogen, and oxygen. Usually. Doesn't have to be. Sometimes it can just be carbon and hydrogen. Sometimes it can just be carbon by itself. But in general, organic things have carbon in it, some hydrogen, some oxygen. So like alcohols have CHO in it. A lot of fossil fuels are just carbon and hydrogen. So kind of depends on what you're working with, but any of these can be considered a combustion reaction. And then the last part is the whole energy piece, and just to add on to what we've done in class so far is there's two paths drawn here. So we have two particles interacting, water and boron trifluoride, so BF3. And if these two were to interact with each other, if they hit each other, they may form a compound down here. Or they may just bounce off of each other and not form a compound here. So there's two independent compounds there. And really what distinguishes between coming down here, forming the compound, and the difference between not forming a compound boils down to how much energy it has in the reaction. So we talked a lot about these energy bar charts. If the thermal energy is at 2 bars, then this reaction may not occur, like the top. But if the thermal energy is at, let's say, 4 bars now, well, now maybe these have enough energy to interact with each other to make that reaction work. If, for example, in the bottom there's excess bars, we know that we are going to transfer those over to the chemical segment of those bar charts. So that's the review for the unit. If you want more examples of the energy bar charts, that's on the other video. That's a little bit more extensive, so make sure to check that out before the test.